Hi, how you doing? You know what I found out? Do you know we're on UWTV? Did you know that? And if you go to, what is it, Channel 27 at 1:30 in the afternoon, you see today's lecture. So this is an alternate, I guess, to web streaming if you want to watch it on television. I want to express my thanks to Hongbo for coming in last time and working some problems on very, very short notice. As you noticed by my absence and probably my appearance today, I'm a little under the weather. I'm heavily medicated, but we'll get through this because I don't want to deny you the pearls of my wisdom here. So we'll go ahead and proceed with the lectures. I did want to announce that we'll have an examination next week at this time in class. The examination will cover the material up through and including Chapter 4. The examination itself will be closed note, closed book, but you're allowed one 8.5 by 11. 8.5. How big is a sheet of paper? 8.5 by 11 sheet of paper on which you can write anything you want to. I need to specify that because about, I don't know, 8 years ago I didn't specify it, and the guy bought in one of these folding computer printout things, and he says one sheet of paper. So I have to specify the size. And he was right, you know. He would have gotten me in a court of law, I think. So one 8.5 by 11 sheet of paper on which you can write anything that you would like. The examination will be all problems, probably around 5 problems, in which you can work. Each of the problems will be equally weighted, and there will be something like a homework, but not nearly as difficult. There is a philosophy in giving tests which I subscribe to, which says the following: if you give problems and they're all easy, guess what happens to your distribution of grades? It approaches a delta function, doesn't it? Your histogram. On the other hand, if you give problems and they're all hard, what happens to your distribution? Your density function. It also approaches a delta function, doesn't it? Right? So therefore, the best tests have a gradient of difficulty, and so I tend to try to do that, to make some very, very easy and then have a gradient of difficulty increasing. Also, there is homework which is due today, and there's homework remaining in Chapter 4. However, I'm hesitant to give you homework and have it due on the date where your test is. So the compromise which I've reached in the past, which we'll do this time, is as follows. I will post the homework and post the solutions simultaneously. So those will both be up on the web today. So this is homework which you do not have to hand in. However, it is homework which you'll be responsible for. Does that make sense? So in other words, you will not hand it in. The content of the homework will be on the test. What I hope to do is to finish the lectures on Chapter 4 by Tuesday, and then have a time in Tuesday's lecture to field any questions which you might have over the material. So please take some time to study before then so that you can ask good questions at that time. Okay? Any questions? Yeah. So it's 1 week from today. I believe it's November 1st. Yes, both sides, and on the edges too. On the margins. Marginals are allowed. Okay. Any other questions? Okay, good. Let's go then to the lecture. Again, I'm not going to talk loudly today because I have a tendency to cough. I took some anti-coughing stuff, and I'm sucking on a Ricola natural herb cough drop. I typically don't lecture with a cough drop in my mouth because it usually inhibits diction. However, I'll do that today. So you'll have to excuse that and chalk it up to adapting as best I can to the circumstances which I find myself in. Okay, let's talk about conditional cumulative distribution functions and probability density functions in 2 dimensions. We were talking last time about 2-dimensional probability density functions, and we ended up talking about line masses. I wanted to talk today about conditional cumulative density functions and probability density functions. Here is the definition of a cumulative distribution function. And it's a cumulative distribution function of x and y, given that x, y lie within a certain area. That's the probability that x is less than or equal to x, y is less than or equal to y. I need my pointer. Okay, I'm going to use a very thick pointer today. y is less than y, given that xy lie in some region in the xy plane. Using the definition of conditional probability, it can be written in this fashion. And I wouldn't spend too much time on these formulas. I would rather invite you to think more about the conditional probability density function. Now, the conditional probability density function is like this. F sub x and y is, of course, equal to the partial with respect to x and y of the cumulative distribution function, which is also conditional. Now, all of this fancy math boils down to a relatively simple explanation, which I'll now give you. And to understand the interpretation of what's going on with the conditional distribution and density functions, we return to our example of the 3,681 trucks. Do you remember that? We measured the length and the tonnage of the trucks, and we came out with a two-dimensional histogram. And we used this to explain the two marginals here, and also the fact that this histogram, once normalized, can serve as an empirical probability density function. So let's take a look at the conditions. We need to put this on the screen, please. Along with this, we need everything, unfortunately. Here's the challenge. We have a probability density function, which is again, we said it was a normalized histogram. Now what we're going to do is we're going to constrain our probability. We're going to say, okay, I'm just not interested in the distribution of tonnage versus length. I want the distribution within certain ranges. So let my density function be restricted in that I'm only concerned with parameters which are within a certain region A, and A corresponds to a region, an arbitrary region on the xy plane. Let's suppose, for example, I'm just interested in A ranging from 1.5 tons to 2 tons, and I'm interested only in length from 9, what do we say, meters to 10 meters. Okay, that's all that I'm interested in. So I'm not interested in the entire range here, rather I'm interested in a specific region of occurrence. So now I want to do things empirically, talk about the probability density function given that my random variable lies within this region. Now here I've expressed it by inequalities. It doesn't have to be with inequalities. I can go over here and actually map out a subregion of my histogram. It doesn't matter. Now, what I've done is in restricting this to 1.5 to 2 tons, that I have restricted the area in the histogram with which I am interested. And it's this new area of the histogram. In order to get the conditional probability density function, using the histogram as my empirical distribution function, I recognize something interesting. First of all, that in the region of interest, this is my region of interest A here in this block, that the shape of the density function, the histogram, if you will, in this region is exactly the same as the shape of the histogram in the entire region, right? If we were to look at these as skyscrapers coming out of the paper, that the amount that these came out of the paper is exactly the same whether I single them out or not. So the shape in here is exactly the same. Now, given, what is the density function given that the random variable exists in here? The conditional density function, or histogram equivalently, is set to 0 otherwise. Thanks, Hungbo. In other words, outside of this region, the density function is set to 0 because we are given that the occurrence of this random variable was in this square. Now, in essence, what we've done is we've come up with a new histogram. Before, our histogram was this big histogram. Now our histogram is this little histogram, and everything else is set to 0 since we're given that the random variable occurs within here. So I start with this little histogram totally from scratch. I can compute the total volume under it and then normalize not by the entire volume of this thing, but just by the volume of the smaller square, right? In other words, to give that the overall area of 1. This is an illustration of the conditional probability density function given that the random variable exists within a certain interval. Let's look at this now interpreted from the probabilistic point of view. We start out with some two-dimensional probability density function, and we are given a region A. We are given a region A. Now, remember that this density function is just like this histogram, except now that every point is a continuous point. Now let's go through the same argument that we applied to the histogram. This density function, not shown here, has some sort of mountain range associated with it, corresponding to come out of the screen at you, and etc. It's a non-negative density function, so it has a shape which we don't see here. But nevertheless, we have given it a region A, so we are assured that the random variable lies within this interval A. So what do? Exactly with the histogram, we assume that it has the same shape within the given region A. Well, suppose this region A has a shape here. This is a three-dimensional perspective here. And what we've done is we have just shown a portion of the density function. Now, the density function for x continues here, but we've only shown the density function, the overall density function in the region A. The second thing we do is we set it 0 otherwise. So it has exactly the same shape in here. It's 0 outside here. And now what do we need to do? We need to normalize this volume so that it has an area of 1, or a volume of 1, I should say. Once we have a volume of 1, then this becomes the conditional density function, following exactly the analogy that we use for the histogram. So let me go through the steps with you again. First of all, we maintain the shape of the given region A here. We maintain the shape of the given region A, number 1. We set it 0 outside of that shape, and then we normalize the volume of what's left so that it has a total volume of 1. Because the conditional density function is a density function. It's still a density function. So therefore it must have an area equal to 1. So let's remember these steps as we go to the math of the next slide. Does this make sense? Okay. Okay, here's the same steps that we had before. And here is what we're saying. If we could scoot this screen over a little bit, thank you. That the conditional density function, given that xy is in A, is proportional to the actual density function for within the region A and is 0 otherwise. It's proportional to the original density function. It has the same shape as the density function. And this C is just a constant of proportionality. What must this constant be? This constant must be that if we integrate this function over the entire xy plane, we must get 0. Correct? So this constant must be equal to whatever gives us a unit volume for this conditional probability density function. And indeed, it's very easy to show that this constant, 1 over c, is equal to the probability that x and y is in the region. And indeed, if we substitute this into this expression, we find out that yes, indeed, this does integrate to 1. But notice what we've done. It has the same shape within the region A, the conditional probability density function. So here's the conditional probability density function. It has the same shape within the region A, okay? Has the same shape means that the density function is, the conditional is proportional to the parent distribution within the region A. That means same shape. It's 0 otherwise, so we set it equal to 0 otherwise. It's 0 outside of that region. And second is normalized using a different number to give us the total volume of 1. So therefore we have to choose a constant so that this integrates to a value of 1, because again, a conditional density function is itself a density function. And this constant then is given by this relationship. So it's a very nice conditional probability density, a nice intuitive insight in conditional probability density functions, which I find useful, and you should too. Okay. Any questions on that? Okay. Now, we're returning to the multiple random variables, and in fact, let me go back because we've done some of the things in the multi-random variables. Because I remember the little boxes. I think we kind of ended up here last time. We saying that if we were independent, if we had independent random variables. Now, of course, we're in an n-dimensional space, and we went through those little illustrations of things which happen in higher dimensions. It's a wonderful, wonderful space. And are you familiar with some of the physics? I'm not an expert in physics, but as kind of a layperson, some of the studies into extra dimensions that currently exist in the area of string theory and such, that during the Big Bang, that there were actually 10 dimensions, and 3 of those dimensions survived with time, and the other 6 dimensions are compacted, and they're part of string theory right now. And compacted means that, have you heard of string theory? It's where you go in physics when you go below the quark. Okay, it's subquark theory. And the motivation for string theory is to unify the forces, and it's a theory which supposedly makes consistent relativity and quantum mechanics. It puts them all together in some fashion, which I don't understand. But anyway, some of in strings, they're actually very small vibrating entities that have extra dimensions compacted in them. And actually, they're 6-dimensional. And they're compacted in the sense that they were never set free, like length, width, and height. And the best explanation that I've read of it, the best explanation, meaning the one that I understand the most, is something like if you have a sheet of paper and you have 2 dimensions in the sheet of paper, if you take that sheet of paper and you roll it into a line, that becomes 1-dimensional. Well, there's actually two dimensions in that rolled up sheet of paper, yet one of the dimensions is compacted. And supposedly in these strings, there's 6 of these dimensions which are all compacted together. So other dimensions indeed do exist, at least in the realms of modern physics. It's more than a mathematical curiosity and a mathematical nicety, which allows us to kind of visualize these higher dimensions. Go here. I'm going to put this in my mouth. I don't want. Why don't you show me putting that in my mouth? Okay. So we have independence, the joint probability density function. And then we had expectation, and I think we ended up showing last time that if we had independent random variables, then the expected value of a separable function. By the way, we should define separable function here because it's kind of interesting. Is equal to the expected value of the product of functions is equal to the product of the expectations. Let me talk about separable functions here. Say, for example, we have a function g of x and y, which is equal to some u of x times a v of y. This is said to be a separable function in the sense that it can be represented as the product of 2 functions. In 3 dimensions, if you have a separable functions, it's the product of 3 1-dimensional functions, etc. Now, the interpretation of this is very interesting. Suppose that I were to have a function of x and y here, and I actually wanted to plot a 1-dimensional function, but I wanted to plot it in 2 dimensions. So I wanted to plot a function of x, but I wanted to plot it in 2 dimensions. What does that mean? Well, it means that independent of what y is, that the function is u of x. So therefore, if I take this value of y, the slice along this, we talked about slices previously of 2-dimensional functions. The slice of the function here is u of x. If we took the slice here would be u of x. So no matter what slice that we take the function at, we get exactly the same function. Therefore, if u of x is equal to 1, see, I turned off my microphone when I did that. You know, on radio, they have a cough button. Do you know that? The DJs have a cough button where if they have to cough, they push it and it cuts off their mic. So I have a cough button down here. Except those listening have no idea what I'm talking about. Maybe, I don't know. Okay, 0 to 1. Suppose that this is u of x. This means that no matter where we slice this thing up here, we get u of x. So what u of x looks like in 2 dimensions is something which is 1 within the slab and is equal to 0 otherwise. Because if I take a slice of this slab and I look at the one-dimensional function corresponding to this slice, don't I get this? Do you visualize that with me? Here's x, here's y, and what we're saying is that this one-dimensional function looks like this, and that no matter where we take a slice, oops, I'm sorry, that's not y. This is u of x. Y actually goes out this way. That no matter what value of y we choose, say we were to choose this value of y, if we choose this value of y, the slice that we get for that value of y, no matter what the value of y is, looks like this one-dimensional function here. So the way that I like to think of these one-dimensional function being separable is as follows, that we take the one-dimensional function and, if you will, we kind of smear it down the y-axis. You see what I mean by smear? And then we take the v of y and we simultaneously smear it down the x-axis, and we multiply those two things together. That comprises a separable function. Needless to say, most of the functions that we look at are not separable, but many of them in elementary math indeed are. So this is the idea of a separable function. Now you might be led to believe that if you have a separable function, that it will have a rectangular sort of aperture, right? A rectangular sort of structure. But indeed that's not the truth. In fact, we saw last time the rectangular density function. We saw a density function wherein, when we had two separable functions, if we smeared one this way and smeared one this way, we got something which was circularly symmetric. And that was which one? It was the solution of the Maxwell's equation, the Gaussian. Remember, if we took e to the minus x squared and we took e to the minus y squared, this is clearly separable, right? It's a Gaussian smeared this way times a Gaussian smeared this way. Yet if we look at the math here, that's e to the minus r squared, where r is a radial vector. It is only a function of the distance from the origin. It's not a function in polar coordinates of the angle. So we can have circularly symmetric objects which arise from, or we can have things which are other than rectangular, let me say it this way, other than rectangular, arising from separable functions. Okay? Question?
Is that the same thing as product form? Pardon? Product form?
I'm not familiar with the term product form.
They use that term in the book.
Oh, they do? Okay.
I don't know if it's the same. That's
I should read the book, I guess. The comment is that this is referred to as product form in the book. Okay. I think you'll find that the term a separable function is more used. Okay. But thank you for pointing that out. So what we're saying here is that the expected value of a function that is separable, notice that the g function, it's a multidimensional function here, but this is a separable function, although it's separable in n dimensions, not 2 dimensions, but n dimensions, that the expected value of a separable function, which is a product of 1D functions, is equal to the product of the expected value of the 1D functions. And I think, did we end up showing this last time? I think we ended up proving this last time. Now, here comes something which is very interesting. If the x's are independent, then the joint characteristic functions are products of the marginals. Wow. What I'm going to do, instead of having you strain your eyeballs, although I guess you have the notes in front of you, right? Or you have the ability to. Again, these boxes are supposed to be arrows. I've asked the Edge office to update our PowerPoint so that those come through. Okay, the characteristic function of the vector x, by definition, is equal to e to the j omega transpose x. Now you look at that, and it looks initially like you're raising a e to a vector or matrix power. Now you can do that. They do that in quantum mechanics quite a bit. But we're not doing that, because in fact omega transpose times x, if you multiply it out, turns out to be a scalar. Remember, you can multiply vectors two ways. You can multiply them together in the inner product, which gives you a number, or you can multiply two vectors in an outer product, which gives you a matrix. This is the inner product wherein two vectors are combined to give us a number. And if we were to expand this omega transpose times x vector out, we would simply get e to the j with the summation of these terms here. So this is the shorthand notation for it. And we can write this, of course. We know that e to the j sum is equal to the product of e to the j's. This is the log. It's what we use in logarithms, right? Natural logarithms. So this expression can be written as the product. Well, in the lemma that we just proved, this is a separable function, right? So the expected value of the product is equal to the product of the expectations. Okay? This again invokes the lemma that we proved on the previous screen. This one. Except now here e to the jk of xk is e to the j omega x. So we have these, and what is interesting then is that each one of these expected values is recognized as a characteristic function of the marginal. So not only do we have for independent random variables the joint being equal to a product of the marginals for independence, we also have the joint characteristic function being a product of the marginal characteristic functions, which is something which is not obvious at all. In other words, we're saying if we have a separable function, I'm not using k here. Let me be consistent with my notation. We have independent if the following is true. In fact, this is a definition, so it's kind of if and only if. We have independence indeed if this is true. And what we have just shown that also as a consequence that the characteristic function of the random variable x as a function of omega, this implies that this is equal to the product of k is equal to 1 to n of the characteristic function of omega. So if they're independent, the density function is separable, equal to the product of the marginals. Similarly, the marginals are separable into the product. I'm sorry, the joint is also separable in terms of the product of the marginals. Where we assume that f sub k of omega k, f sub k of xk, has a characteristic function of this. They're related by one-dimensional transforms. So many of the things which you have learned in one dimension are readily adaptable in higher dimensions under the assumption of independence, because now you just take your one-dimensional results and you multiply them together if things are independent in order to obtain the results. So again, the important thing here is that if the random variables are independent, then the joint is equal to the product of the marginals in terms of density function, and also the joint characteristic function is equal to the product of the marginal characteristic functions also. So on this screen we have, if you will, a proof of this proposition. Now let's look at a very interesting result. Let's suppose that x and y are independent, and let's let z is equal to x plus y. Is that okay? Z is equal to x plus y. Now, in this case, the characteristic function of z, of course, is equal to the expected value of e to the j omega z. You agree with that? That's just by definition. But z is equal to what? Z is equal to x plus y. So if we substitute x plus y for z, we get this expression. With me? Now with this expression, this is actually separable functions. This is a separable function, and we can actually write this as a separable function of x and y. So we can write this using our lemma that we just proved as the product of the expected values. Now each one of these products is the marginal. So we come up with a very interesting result that if x and y are independent and z is equal to x plus y, then the characteristic function of z is equal to the product of the characteristic function of x times the characteristic function of y. Now, the reason that this is interesting is because of our electrical engineering background. We know that when we multiply two things in the frequency domain, what do we do in the corresponding time domain, or x domain in this case? We convolve, don't we? So indeed, if we go back and do an inverse Fourier transform, then the density function for z is equal to the density function for x convolve with the density function for y. And indeed, this is what happens for independent random variables, and this is what we have here. So we have the definition for the characteristic function, I'm sorry, for the density function of z is equal to a convolution, and this is the convolutional integral written out in longhand, which is something that most EEs learn as sophomores, juniors, sophomores? You don't know, do you? You learn it early, though. It's fundamental. Now, we learned last time, or I gave you an illustration last time of the case where we had two die. Remember that? If we rolled one die, we got a uniform density function. If we rolled another die, we got another uniform density function. And if we rolled two die, remember we got the triangular density function? And then my proposition to you was, look, this triangular density function is indeed equal to the convolution of these two uniform density functions. So that was an illustration from everyday life that indeed this convolution property does hold. And so we have proved it, albeit in somewhat more of a formal setting. Now suppose this extends to higher dimensions. If this extends to higher dimensions, let's look at the case of x sub k, our IID. Now IID is a very important concept that we haven't talked about yet, and we'll be using it a lot. IID, when we use this, means they're independent and identically distributed. That's what IID means. So if we have IID random variables, each of the random variables is independent, and each of them is described by the same probability density function, okay? So if the first one's Gaussian with a parameter of sigma is equal to 1 and mu is equal to 1, that means all of them are Gaussian with a variance equal to 1 and a mean equal to 1, okay? So that's what we mean by identically distributed. Independent means that each of the random variables in the sequence, and we'll typically talk about n random variables, you can see the n here, that each of the n random variables is statistically independent from the other random variables. So this is what we mean by IID. We'll be using the term quite a bit. Now, where do you get IID random variables? Usually you get them from repeated trials. The source of IID and the place that they're used a lot in engineering is from repeated trials. For example, you take a voltage reading off of a resistor that's being fed by some sort of noise. Well, you take one reading, you take another reading, you take another reading, you take another reading. Well, if your noise source isn't changing, then you can assume, maybe a good assumption, might be that all of your measurements actually came from the same probability density function, right? And they're also independent of each other. So that would be an example of an IID random variable. Another example is we roll a die n times. Each time we roll that die, the density function is that uniform density function, correct? And they're independent of each other in the sense that the outcome of one roll of the die is independent from the other roll of the die. So that's another example of IID random variables. Let's look at what happens when we sum n IID random variables. It's really fascinating. We take a sum from k is equal to 1 to n of x sub k, and these x sub k's are assumed to be IID random variables, independent and identically distributed. Generalizing the result that we had last time, the characteristic function for the sum is equal to the characteristic function for x raised to the nth power. Let me elaborate on that. This is the characteristic function that we seek, right? It's a characteristic function of the sum. This is equal to the summation of the IID random variables. We know that this is the same thing as the expected value of the product. right? Now, this is k is equal to 1 to n. Now, up to here, it's been very general. Now we're going to impose independence, because with independence, the expected value of the product is the product of the expected values. So we have imposed here independent. If they weren't independent, we couldn't take that step. Because they're independent, we can we can take this step. Now, each one of these is recognized as the characteristic function of the kth random variable as a function of omega, right? I'm sorry? Yeah, it should be. Thank you. This should be a pi. So that's equal to the product of these individual random variables. Now, we've used independent here. Here we're going to use the identically distributed. Because if they're identically distributed, all of these characteristic functions are going to be exactly the same. If they're identically distributed, they all have the same density function, therefore they have all the same characteristic function. So we're multiplying a function then, and all of these functions are equal to each other, and we're multiplying that function by itself n times. What does that give? That gives the characteristic function for x. We don't even have to subscript it now because they're all the same. Characteristic function for x1 is the same as the characteristic function for x2, the same as for x3, etc. So we multiply it by itself n times, so we obtain this result. And this is the result that we have on the slide, which I just showed you. Any questions on that? Okay. Let's go back then to... Now here's something which is kind of interesting. We can use this relationship, and I think, let's see, do we do that? We can use this to show that if S is Gaussian, if the S sub k's are Gaussian, that S is Poisson if the S sub k's are Poisson. Sum is binomial if the X sub k's are binomial. This is really, really interesting. Let's take a look at this, for example, and we will revisit this a little bit later when we talk in the next chapter about summations. Let's suppose that we have a sum is equal to the summation of k is equal to 1 to n of x sub k, and say each x sub k is distributed as a normal random variable with a mean of m and a standard deviation of sigma. And we're going to add these up. Well, if you were to look at the characteristic function for a Gaussian random variable, you would find out that it was e to the j omega m minus 1/2 sigma omega squared. That's equal to the characteristic function for a Gaussian random variable with a mean of m and a standard deviation of sigma squared. According to the result that we had here, the characteristic function of the sum is equal to what? It's equal to the characteristic function of an individual random variable. I probably should put this as x here. It's equal to the characteristic function of a single random variable raised to the nth power if I do a summation of them, right? And then what this is equal to is very interesting. This is equal to e to the j omega n times m minus 1/2 n, by the way, this should be a sigma squared here, n sigma squared times omega squared. You agree with that? And then what is incredibly interesting about this is that this is a probability, this is recognized as the characteristic function of a random variable, a Gaussian random variable, with a mean of what? Instead of m, it has a mean of n times m. right? And instead of a standard deviation of sigma, it has a standard deviation of root in sigma. Is that okay? So the fascinating thing is that if we add a number of Gaussian random variables, we obtain a Gaussian random variable. Now, the mean and the standard deviation of that Gaussian random variable are different than each other, right? They're different. The distribution of S has a different mean and variance than the individual x sub k's, but still it's a normal random variable. So in other words, the normality or the Gaussianness of the underlying random variable has been preserved, even though the parameters have been changed. Isn't that interesting? And what I am saying is if we get back to this, we'll actually show this later when we get to the chapter on sums, that if S is Poisson, then the x sub k's are Poisson. In other words, if you add a number of IID Poisson random variables, you come up with a Poisson random variable. The parameters of the Poisson are different. The parameters are different, but the values, but it's still a Poisson. It's true for the binomial, the gamma, the Cauchy, and also the negative binomial. Interesting. Let's do the Cauchy, because this is kind of an interesting one. I think that you showed for a Cauchy that the characteristic function was equal to e to the minus beta times x or omega, where beta is some sort of parameter of the Cauchy random variable. That's equal to the... By the way, you recall that we said that the Cauchy random variable had an undefined mean and an infinite variance? You remember that? We can also see this from the characteristic function. How do you get the mean of a characteristic function? What you do is you differentiate it, right? And then look at the value at the origin, right? You'll notice that this doesn't have value at the origin, because if we look at the first derivative of it, we obtain something which looks like this. That's the first derivative of that Laplace. What is the value of this at the origin? That's not defined, is it? You might be tempted to say, okay, well, I'll take the midpoint of the discontinuity, in which case you get 0. But what is very interesting is to get the second moment here, which we also saw was a big problem. To take the second moment, we would have the original Laplace, plus we would have a delta function which went down here to minus infinity. Don't forget we flip it over to get the second moment, so the second moment is equal to infinity. So you can see what is the second derivative evaluated at the origin. It's infinite, or minus infinity, right? So therefore the second moment doesn't exist. So we not only saw this by evaluation of the integral for the Cauchy, but we can also see this in the characteristic function. Very interesting result. Now, let's look at the case where we have some n IID random variables, and we take a look at the summation of k is equal to 1 to x of x sub k. What we agreed is if they were IID, then the characteristic of the summation was equal to the individual characteristic function raised to the nth power, which in this case is e to the minus n beta times omega. Correct? So you'll notice that this also is a Cauchy random variable, isn't it? Up here, the Cauchy random variable had a parameter of beta. Here it has a parameter of n times beta. So the parameter of the Cauchy is different, but it's still Cauchy. So the Cauchiness, if you will, is preserved in the summation. And the big list that I gave you here are different types of random variable where the type of random variable is preserved upon the summation. Not only the Gaussian and the Cauchy, but the other ones that I listed here. And I invite you to look at the characteristic functions, for example, of the Poisson and the gamma, and maybe the negative binomial, which I've given you in the PowerPoint slides that you have. And maybe take a look at a couple of those and raise them to the nth power and convince yourself that indeed the type of random variable is conserved, even though the parameters of the random variable have been changed. I think right now would be a good time to ask if there's any questions. And if there are no questions, let's go ahead and have a break and meet when the big hand's on the 6 again. Thanks. They should outlaw those squeaky shoes. Seems to be a way to get around that.
Outlaw the rain, and that's what happens, right?
Yeah, but it seems like a good engineer could get around squeaky shoes. What would you do if you worked for Nike and your boss came to you and said, get rid of the squeaky shoes? Now, you couldn't put oil on it because you'd probably get up to a bunch of lawsuits, right? Because you'd slip on it.
You have to put something that didn't wear off as quickly as the rubber, and that wouldn't be very good.
Latex. You think latex is
Traction,
latex
no.
sweet? It's a good engineering problem. These are good qual. One of the qual exams we used to give is, you ever see that foam rubber that looks wavy that they use for packing material? Question is, how do they make that?
Double equality.
This is double equal. I've heard profs say, why are manhole covers round? These are kind of the Microsoft interview questions that you get. These very strange ones. So that's a good one. Anybody know? Huh? But how do they make how do they physically tool that foam rubber?
It's not really a wave, it's like three-dimensional wave.
Yeah, it's a three-dimensional wave. Right.
Just make sure.
Yeah, it's a three-dimensional wave. It's like little bumps. And then the hint that they give is there's another piece that goes exactly mesh with it. Right, they fit exactly with each other. So clearly they take one piece and they cut it out really easily. A standing wave?
I'm sorry. They cut it twice, maybe? Like one like
It has to be separate. Oh, don't make me laugh. Excuse me.
Thank you. Okay.
You're welcome. I'll try to turn off my microphone when I do that. Okay. Anyway, let's get back to this. Did you figure out the derivative of the integer yet? Or did I tell you? Yeah, the derivative of n squared. Oh, I didn't give you that. I didn't tell you the solution, though. Right? So you figure that out, and I'll tell you how they cut the foam rubber. Okay. Because you should know the derivative. I don't know about the foam rubber. Oh, I'll tell you. Once you hear it, you go, oh yeah, of course. It's one of those things. What you do is you take the foam rubber, and you have fingers which go in from both sides. Push it together, out of phase, then you cut straight across when the fingers release. Obvious, right? Okay. Okay, functions of several random variables. Let's talk about, we've talked thus far about a function of a random variable. For example, you measure x, but you don't want x. You want the log of x, or you want x squared. You want g of x. We have sorry for the cough button. Some of them sneak up on me, man. It's kind of hard to censor them. So we looked at that for a single random variable. Now, it might be in terms of a multidimensional random variable that you have a vector of x. You want to operate on that vector of x to give you a single number out. We've already looked at a case of this where the g of x was equal to the sum of the values of x. That's an example of a linear combination. But what about in the more case of a nonlinear combination? Suppose, for example, we wanted to look at the sum of the squares of the x's, or we wanted to look at the sum of the log of x's, or some other function of the individual random variables. The question is, given the density function for g, how do we find out the one-dimensional density function for z? Again, we've done this for the case where g is equal to a single sum, x1 plus x2 plus x3. In that case, we perform the computations using the characteristic function. So this is one. This is a single function of a random variable. So z is equal to g of x, the sum of the squares, sum of the logs, the product of the random variables. And then there's functions of n random variables. Suppose, for example, you have x. This is a vector x, and you're operating on it not by one random variable or one function, but k functions. And you get a new random variable z. For example, suppose x is a vector, and this g operation is a matrix operating on that vector. say A times X, a matrix operation. So you're going to get a new vector, which is called Z. If you know the joint density function for the random variable X, what's the joint density function for the random variable Z? Now, the matrix equation that I mentioned is one example, but we're kind of interested in just general cases. So we're going to look at two. We're going to look at a single function of n random variables. In the case where we take the n random variables and collapse them into one random variable, we'll look at that first because that's more straightforward. And then we'll look at functions of n random variables where we take n random variables and we generate n additional random variables from those component random variables and see what happened to the probability density functions in doing so. In doing this, it's going to be important to use Leibniz's rule. Leibniz, of course, is the one who sparred with Newton on credit for inventing the calculus. Newton was a really interesting guy. One of the things, he was a nerd. He was kind of a nerd. He used to, when he was a kid, he was trying to study colors. So he said, there's something in colors. And he found out if he looked at the sun and then closed his eyes, he would see colors. So he did that a lot and just about went blind in looking at colors. But it's also said that he would attend parties and things and start to think of equations and some of the theories, and he would just separate himself totally from the party and just sit down and do the calculations. But he was also very secretive in what he did. Much of his work he put in a drawer and actually didn't publish, and this indeed contributed to his sparring with Liebnitz over who invented the calculus, because Newton had indeed done it earlier, but he just hadn't been as forthcoming in the publishing of his work. Liebnitz, by the way, invented the notation that we use today for the calculus. Newton's calculus had a different notation, and for some reason we use Leibniz's notation today. And the reason I don't know, because I don't know what Newton's calculation or Newton's notation was. Anyway, here's Leibniz's rule. Again, we have a font problem here. This dot, hopefully on your notes, printed out as a script L. Is that correct? Okay. So this should be, instead of dot of z to u of z, this should be script L of z. The L was kind of stood for lower, the lower limit of the integral to the upper limit of the integral. But what we have here is we want to differentiate a function whose limits of integration are a function of z and whose integrand is a function of z. Leibniz's rule allows us to do this. And it's kind of a generalization of the chain rule with a little twist thrown in. It turns out that the derivative of this expression is equal to the derivative of the upper times the integrand with x replaced by the upper limit minus the derivative of the lower times the kernel with L, and then plus the same integral but with the derivative taken in the inside of the integral. Now we'll use Leibniz's rule because it turns out to be very, very handy in some of the stuff we're going to do. We'll primarily use these two properties. We will not typically deal with an integrand that's a function of z. In other words, the integrand will only be a function of x. If indeed the integrand is only a function of x, then this final term disappears, doesn't it? Because the partial with respect to z goes away. So we'll probably look primarily at Leibniz's rule for the integrand only a function of x, not a function of what we're differentiating. He anticipated computers. It is unworthy of excellent men to lose hours like slaves in the labor of calculation which could be safely regulated to anyone else if machines were used. Okay, let's take a look at one function of several random variables. Now, don't forget how we characterize this random variable. We characterize it in an n-dimensional space, and in this n-dimensional space we have an n-dimensional probability density function specified. We can interpret the probability density function in 1 and 2 dimensions, a little bit in 3 dimensions, but we lose it in 4 dimensions. Nevertheless, in higher dimensions, this value of x is such that that every point in this higher dimensional space has a number associated with it. That number is equal to the value of the probability density function there. Okay. So we have z is equal to g of x. This is the result that we're doing. Here is a general methodology to determine the probability density function of z. Actually, we won't determine the probability density function first. We'll determine the cumulative distribution function. We determine the cumulative distribution function by starting out with the definition of finding the distribution function, the cumulative distribution function of z, which is the probability that z is less than or equal to z. Okay? And then it's simply a matter of substituting g of x in there. What we will find is that once we substitute this value of g of x in here, that this will translate to a certain region in the space or in the plane that we're interested in. And the challenge is to find the region for which this is true. But this is a general methodology. We'll illustrate it using different ways. But we need to find a region in the space. For example, for a given value of z, the probability that g of z is less than or equal to z might correspond to this region, right? We can evaluate inequalities and actually specify regions in the space. If we can do that, if we can find a region for which g of x is less than or equal to z corresponding to this region here, the probability that this is true is simply equal to the integral of the density function over this region, right? Because that's a probability that anything is true. So that's the situation that we have. Let's illustrate this through some examples. Here is a restatement of what we talked about before. Here's the distribution. Here's the region. And of course, the density, the distribution function then, is equal to the integral of x over this region. And by the way, this region is a function of z. If I change my value of z, this region is typically going to change. But for a fixed value of z, it's a fixed region. And I have to evaluate it for all different, the entire family of curves corresponding to different values of z. So, no, it does not necessarily. The question is, does it necessarily have to be a single region? Absolutely not. The regions can be disjoint. Absolutely. So, if we integrate over this region, then we will obtain the distribution function for z. And this is one methodology for determining this. And of course, once we get the distribution, we can find the density function by performing the derivative of the distribution function. Let's take a look at the sum of two random variables. Now, we've actually looked at this before for the case where the random variables are IID. This was the case where we talked about the characteristic functions, recall? But now let's talk about it applied to the methodology that we are talking about. Let's first of all talk about the region. Well, here's the region that we're talking about. Here is the density function for x and y. And we want to find out the region for which x plus y is less than or equal to z. So this becomes the region of integration. By the way, in all of the things that we're doing, the region of integration will be denoted in yellow here. So if we go back here, for a specific value of z, the region is r sub z corresponding to all of the points below this line where we have a 45-degree line intersecting x and y both equal to z. So if as z changes, this just moves up and down the axis. Okay? So this is the distribution function. The probability that z is less than or equal to z. It's a probability that x plus y is less than or equal to z, which is a probability the random variables lie within this shaded yellow region. And then if we apply our advanced calculus to perform this integration, we get the integral from y is equal to minus infinity to z minus x, as you see here. So this is the expression that we obtain by integrating over the density function to find the probability the random variable lies within this region. Okay? Well, this is a repeat of this result, but what we're interested in is the density function for this. We obtain the density function by differentiating this result. So if we differentiate this result, you can see immediately the application of Liebnitz's rule, right? Since we are differentiating as a function of z an integral whose upper value is the function of z. So we take the derivative inside the x integral and we operate it on it in the y integral, and we obtain the following by application of Liebnitz's rule. We find that the density function of z is equal to this single integration that we have here. Now, this integration that we have is the formula that we obtain when z is equal to x plus y, and we want to find the density function for z given the density function for x and y. And it's very general. There's no assumption of independence. There's no assumption of identically distributed. This is applicable for any x plus y. Add apples and oranges if you wanted to. Now let's look at what happens, very interestingly, if x and y are independent. What do we know if x and y are independent? Then we know that the joint density function is equal to a product of the marginal density functions, correct? So if we were to take that same exact integral, except now in the integrand we're going to write it as two functions separable to each other, we obtain the integration which is shown here. So this is exactly the integration on the previous page, but now we're imposing independence on them. And notice what we get. We get the convolution, which is exactly the result that we obtained looking at the characteristic functions. So we have independently derived this convolutional property of adding two independent random variables together and having that correspond to the convolution of their density functions, and we have derived it in two ways. We've derived it by looking at the characteristic function, and number two, by looking at this more general methodology. Isn't that interesting? So now you've got to be a believer. Well, let's take a look at some other things that we haven't seen before. Let's take a look at the product of two random variables. The product of two random variables. Say z is equal to x times y, not plus, but x times y. I think you can see that we have a whole bunch of different combinations that we could actually do combining x and y. For this explanation, we're going to assume that both the random variables x and y are non-negative. In other words, something like an exponential random variable or a gamma random variable. If we allow the random variable to go negative, it becomes a little bit more complicated. So I think for pedagogical reasons, we'll just keep x and y being non-negative random variables for our discussion now. So z is equal to x times y. So therefore, z is also going to be non-negative, right? Okay, well, let's take a look at this. Again, what we need to do is we need to look at the distribution function for z and ask ourselves, what is the distribution function according to the definition? It's the probability that z is less than or equal to z. Okay? And of course, in this case, z is equal to x times y. Now, because I have restricted my random variables to be non-negative, I can take my x to the other side without disturbing the inequality. So you can see the utility of my assumption here. If I didn't do that, I would have to look at one term for when it was less than 0 and one term for where it was greater than 0. But in general, if it's greater than 0, I can take it to the other side. Now this then defines the region in my xy plane over which I want to integrate. Because if I look at the region that y is less than or equal to z over x, that corresponds to this hyperbola, and the area of the density function below the hyperbola in the shaded area. Because in this region, right on the border, first of all, y is equal to x, or z over y. And by the way, as z changes, my hyperbola changes, but it basically has the same shape, right? And so what I would like to do is I would like to integrate my two-dimensional probability density function over this yellow region bounded by the hyperbola in the first quadrant. Because I've restricted to non-negative cases, I only have to integrate over the first quadrant, which is kind of nice. So the integration, if I apply my integration over that yellow region, I obtain the following relationship. I want to integrate, let's see, y. I'm going to integrate y from down here to the top to when it hits the hyperbola. It hits the hyperbola z over x, right? and then I want to integrate all my values of x from 0 to infinity. So does that make sense? So this is the distribution. Again, I look at the definition of my nonlinearity, and I integrate. I find a region corresponding to it, and then I integrate over that region. So in this case, my integration is as is shown in this equation. Of course, this is the distribution. In order to find the density function, I need to differentiate that distribution function. Here again, I use Liebnitz's rule, because the derivative of this, I take the derivative with respect to z past this integral sign, and we have the derivative with respect to z of an integral whose limits are a function of z. But notice the integrand is not a function of z. So again, as advertised, that term in Leibniz's rule is one that we don't use here. So if I apply that, I get the following. Here we've taken the d dz inside. We've applied Leibniz's rule by differentiating the upper limit times the lower limit evaluated where the upper limit is. And so this is the result that we obtain. So if I have, in summary, a two-dimensional probability density function, and z is equal to x times y, and I want to find the density function for z, I need to look at my joint probability density function and evaluate this integral. Once I evaluate this integral, I obtain my density function for the random variable z. Now, unlike the summation, there's really no nice simplification that comes out assuming the random variables are independent here. Usually random variables being independent are only useful in performing weighted sums of random variables, because then you can use the separability argument. In other transformations of the random variables, such as this product rule, they're not very, independence doesn't help you a lot. Let's take the product of, excuse me, two random variables. Z is equal to x times y. Let's just assume that x and y are IID and uniform on 0, 1, just to do something. Here's our general statement of our density function for z. So this would be in MATLAB. You generate two random numbers, uniform on the interval from 0 to 1. You multiply those two random variables together to get a new random variable. What's the density of that new random variable that you obtained by multiplying those two uniform random variables that you're going to generate on MATLAB? Here's the general formula. We need to apply the case where x and y are IID and uniform on the interval from 0 to 1. So let's look at the density function, f of xy. By definition, it is equal to 1 for for x between 0 and 1 and y between 0 and 1. That's the definition of the density function for that two-dimensional random variable. Do you agree with that? So it's a little box on the two-dimensional plane. Now, in order to get the integrand here, we don't want this, we want this. Well, how do we get this from this? We simply take wherever there's a y and we substitute a z over x in the mathematics. So what I've done in order to obtain this is I've written out the definition of what my original function is, and then every place I see a z, every place I see a y, I substitute a z over x, which is what I did here. So I obtain this, and then if I simplify this inequality, I find out that f of xy is equal to 1, but you'll notice that z has to be between what? 0 and x, correct? If I take the x to the other side. Now, can I take x to the other side? Yes, because it's non-negative, because I'm only dealing with the random variable in the first quadrant. So I can take this x to the other side. So z has to lie between 0 and x has to lie between 0 and 1. So this is the density function corresponding to the integrand. What I need to do then is, once I have this integrand, is interpret this interval in terms of this integration. Here's a repeat of what I had on my previous slide. And now to interpret the integration is equal to the integral from x is equal to z, because you'll notice that z has to lie between, x has to lie between z and 1. So therefore, x, I'm integrating x between x is equal to z and x is equal to 1. If I do this, I have a density function which is minus the log of z, which is really interesting. If you multiply two independent unit variants are random variables uniform on 0 to 1, you obtain a density function which is minus the log of z. One thing which is interesting about this is that the log of z goes to infinity, doesn't it? Which is very interesting. It goes to infinity. And we might at first be skeptical about a density function that goes to infinity, but there's really nothing in the rules that we define the prohibited density function of going to infinity. The only thing we said, it has to be non-negative, and it has to have an area of 1. That's all we said. And this is non-negative, and does it have an area of 1? Is the question. Can something which goes to infinity have an area of 1? Well, yes, it does, and I'll show you just a quick way to think about it. This is the density function that we described. This is our density function for z. And the question is, what is the area of this? Now, you could evaluate it by going to an integral table and convince yourself, but maybe an easier way is to turn this thing sideways and look at the inverse of this function. The inverse of this function is e to the minus x. And you'll notice the shape of this, if we twist it and turn it, is exactly the shape of that, right? And e to the minus x is very easy to show has an area of 1 from 0 to infinity. So we have simply taken an e to the x and we have kind of turned it sideways, and this still is going to have an area of 1. So yes, indeed, minus log of z does have an area of 1. It's a very viable probability density function, and just because it goes to infinity, we need not worry. It's no problem. Everything's fine. Copacetic. Okay, let's take a quotient of two random variables. Suppose z is equal to x over y. We're going to do this differently. Remember we said in general, the more general of a methodology you apply to solution of a problem, typically the more cumbersome it is. Remember that? So if you can find a better way to do it, a short way, then you're going to have an easier life. So we're going to do this a little bit different. We're going to go through the back door a little bit by, first of all, reminding ourselves of the scaling theorem, the scaling background. So eventually we're going to go to this problem, but before we do that, we're going to go down a side road and kind of look at a lemma where y is equal to a times x. This is the result that we obtain. This is a result that we have seen before. If y is equal to ax, then the density function for y is given by this. If a is greater than 1, it means it's stretched out by a factor a and pounded down by a factor of a in order to preserve the overall area equal to 1. Now, if this is equal to the density function for x and say a is equal to 2, then that's the density function for y. It's spread out by a factor of 2 and pounded down by a factor of 2. So, given y, this is a simple scaling problem. Let us let a is equal to 1 over y. Now, a before was a deterministic number, right? But now let's let it be equal to the reciprocal of y and ask ourselves, what is the density function of z given y? Well, the density function, if we're given what y is, it's exactly equal to the previous result, where instead of a, we substitute a 1 over y. Okay? So if we go back to this definition, and we simply substitute a is equal to 1 over y, we get a conditional probability density function. And this is exactly this previous result, except that instead of a, we are given y. And indeed, given y means that we know what y is. So y in this expression is deterministic. It's something which is given. So this is a totally viable result. So this is the result that we get. This is a repeat off of the previous slide. The density function for z is a function given y. And now we take advantage of the joint density function, where we obtain the joint density function from the conditional times this relationship, following immediately from Bayes' rule. Well, we know what this is, and we know what this is. This is the marginal. This is the uniform distribution. So simply substituting in this relationship into here, we can obtain the density function for y as the density function for z as a function of the quotient of x and y, as we see here. So this is a backdoor derivation. So again, if we're given the joint density function of y, of x and y, and we want to form the quotient, given the joint density, we can come up with the density function for z very easily. And that's the final equation that we have for the density function of z. And again, this did not apply the general methodology that we use. This was a totally different, using conditional probabilities, and just shows an alternate way to derive, in this very specific narrow case, the density function for the quotient of two random variables. Let's take the case where x and y are IID exponential random variables, just to show you a case where this works out. So here's the joint density function for y, x and y. We need to substitute this into this expression. Doing so, if we substitute this into here, we obtain this expression that we need to evaluate in order to determine the density function for z given x and y. And we can evaluate this integration relatively easily by looking at this integration and then just applying some, I do it kind of unconventionally here, but you can apply integration by parts. I think is probably the most straightforward way of doing it. I did a little bit different here. So indeed, if we have two exponential random variables and they're IID, and we divide one by the other, we get this as the density function, which is what? A Cauchy. So two exponential random variables, one divided by the other one, gives us a Cauchy random variable. Well, not a Cauchy, half a Cauchy, because it's times a unit step. It's a Cauchy with the negative part cut off. Can you tell me, do you think this has a finite or infinite second moment if we cut off the positive value? Is it still infinite? Cut off the negatives. I say cut off the negative. Cut off the negative. Yeah, it's still infinite. It's still infinite. Both sides of the integrand become infinite. So if you cut off one, the other side still goes to infinity, and you're out of luck. What was that? I don't want that. Go away. Go away. Okay, good. Fascinating. I want to talk to you about generally finding expectations of random variables. Suppose that you wanted to find the expected value of z where z was equal to a function of x. There are two ways to do this, a smart way and a dumb way. I'm going to tell you what the dumb way is. The dumb way is to compute the density function for z, which was what we've been doing, and then find the density function for z and then compute the expected value of z by this formula. The reason that that's the dumb way is the only thing that you wanted was the expected value of z. To obtain that, you had to do a whole lot of unnecessary work to find the density function for z, and you don't need to do that. Okay, you don't need to do that. Rather, the smart way, usually, there's always exceptions, but generally if you want to find the expected value of z, you just recognize it's the same thing as the expected value of g of x, and you integrate over the joint density function of g of x times f. There's no reason that you need to compute the density function for z if all you want is the expected value of z. Let me give you an example. Suppose x was a normal random variable with a zero mean and a standard deviation of sigma, and y is equal to x squared. The question is, what is the expected value of y? Now, one way to evaluate the expected value of y is to go back to the stuff we looked at in the previous chapter, compute the density function for y, and then find this by integrating y f sub y of y, well, yeah, f sub y of y dy. We could do that. You see, we could do the transformation of a random variable. We could find y and then substitute it into this formula. That's fine. But the expected value of y is also the expected value of x squared. The expected value of x squared can be written as the integral of x squared times f sub x of x dx, where x is your original Gaussian. Well, this is the second moment of a Gaussian random variable when the mean is equal to 0. Right? This is the second moment of a Gaussian random variable when the mean is equal to 0. This is equal to sigma squared. Okay? It's equal to sigma squared. Notice that I had, in order to get this answer, because the only thing I wanted was the expected value of y. I didn't ask you for the density function of y. I just wanted to know what the expected value of x squared was. So I don't need to compute the density function for y and then compute this integral. If I did, I would get this result. If I did, I would get this result. But don't you think that instead of evaluating it this way, it's much easier to evaluate it this way? Because we have avoided unnecessary work and the unnecessary work of computing this density function for y. And this is generally the case. There are, of course, exceptions, and you have to look at the problems because you're going to be seeing the exceptions. But generally, it's much easier to actually compute the expected value this way as opposed to computing the overall density function for z, or in this case, y. Here's a simple example. Suppose that x and y are uniform over 0 and 1, and they're IID, and we want to find the expected value of z when z is equal to the cosine of 2 pi x plus y. Oh, good grief. You know what this means if we actually computed the density function for z? That would be a hard thing to do. Probably 2 or 3 sheets of paper to do this sort of thing. But if we're just interested in the expected value of z, we can substitute in the original density function, which is 1 on a unit square, and integrate this out, and we get 0. So this one little step allows us to get the expected value of z without computing the density function for z. If the random variables are discrete, we can apply the expectation as we did in the continuous case, except, of course, the integral now becomes a summation. Since for discrete random variables, our probability are totally in point masses. Oh, this is terrible. Okay, the joint moments of x and y. We know what the moments of a single-dimensional random variable are. We know that the first moment describes the central tendency of the density function, and the second moment, normalized subtracting out the first moment, is the measure of dispersion or the variance of the random variable. Here are the general definitions of the moments of a random variable. Visualize this dot as a script L, because that's what it's supposed to be. We like to use a script L because the regular L looks like a 1, and we want to avoid that. So that was a script L. Tried to be fancy, didn't work. So this is x to the L, y to the k, and it's equal to, by definition, this value. And the expected value of x to the L, y to the k is referred to as the joint moment of x and y. And similarly, there's an expression for when the random variables are discrete. We simply perform a summation as opposed to the multiplication. Dealing with 2 dimensions, there's some very important random variables very important expected values. So we have a random variable x and y. We have the expected value of the product of x and y. If this is 0, x and y are said to be orthogonal to each other by definition. If the expected value of x times the expected value of y is equal to 0. The covariance of x and y is equal to the expression here. You'll notice that if x is equal to y, the covariance becomes the variance, right? If x is equal to y here. So this is kind of a generalization of the concept of variance, except now it's being applied across 2 random variables, x and y. And then there's a very important correlation coefficient, which is the ratio of the correlation to the variance. And the correlation coefficient lies between -1 to 1, and many times in linear models is used in statistics to tell you the relationship between one random variable and another one. However, as we'll see when we talk about the Gaussian random variable, this assumption is only true when your random variables are related in a linear fashion. So that's your correlation coefficient. You might have heard of some of these. Okay, we'll leave you, I think we'll call it a day here, with this mammoth expression, which is the expression for a two-dimensional probability density function for a Gaussian random variable. The Gaussian random variable has parameters of the mean in the x direction, the mean in the y direction, the covariance, sigma 1 in the x direction and sigma 2 in the y direction. We will look at this and spend some time and become friends with this equation when we next meet. Any questions? Okay, thank you for your time and for enjoying my cold. Bye-bye.